So how do we know any of this stuff is true, right? Because I could be making all this up. And the reason we know this is true is through spectroscopy. We know that if the energy levels or the energy states are there, as we come in with a photon, right, if it has exactly the amount of energy to boost our state from a lower level to an upper level, then that will be absorbed and vice versa. And so we can actually drop down from an upper state to a lower state. And if we drop down from an upper state to a lower state, then that emits a photon. So we know the energy levels are here because we can feel the photons being absorbed going from one level to the other. So what are some other factors that need to be true for us to see rotational spectroscopy? So it turns out that not all molecules actually have a rotational spectrum. Molecules have to have a couple of things. So one is that the molecule must possess a permanent dipole moment. So it has to have a dipole moment, an electric dipole moment to be technical. And if it doesn't have a dipole moment, it is not going to have a rotational spectrum. So what are some examples of molecules that have a dipole moment? Well, we know HCl. The two atoms have very different electronegativities, and so that gives us a permanent electric dipole moment pointing from the H towards the chlorine, unless you're a physicist, in which case it points in the other way. And if we take a molecule like hydrogen, though, hydrogen does not have a permanent dipole moment. So, in fact, if it vibrates, it doesn't have a dipole moment either. Some of these other molecules, though, they vibrate. They may take on permanent dipole moments. We'll see that's important later. But for now, if we take a molecule like carbon monoxide, we can see it is also going to have a permanent dipole moment. So we'll see a rotational spectrum. However, something like carbon dioxide, we're not going to see anything. And the reason we don't see anything for that is that it's a linear molecule. And though each bond might be quite polar, and so each bond may absorb infrared light and cause a vibration, the rotation is actually not something that we see. So the dipole moments cancel out. So it has an overall dipole of 0. So CO2 does not give rise to a rotational spectroscopy spectrum. So not only does the molecule itself have to actually have a dipole moment, when we do these transitions, we have what we call a selection rule. So not all transitions are allowed. Although you have multiple levels, you are only allowed to jump up or jump down one level at a time, which is to say that delta J can only change by 1 unit. So that means, if you've got J equals 22, and you want to absorb light, then you can go into the J equals 23 level. But you couldn't jump up to a higher level, let's say like 24 or 25. That's just not going to happen. So you have to have a change in rotational quantum number of plus or minus 1. And of course, positive 1 means you've got an absorption because you're going up in energy. And negative 1 would be an emission, you're going down in energy. We'll probably focus on absorptions here, but emissions are just fine too.